first I will present myself. I'm Araldo, and I'm late to the conference at Télécom SudParis. The office is very close to here. And the title of my talk is Collective Behavior Emerging for Multiple Agents in Networks. So I will talk about nothing new. These are very classic results. But I think it's nice to review these classic results. At least for me, this was an occasion to revise these classic but very insightful results. So I will talk in general about networks. And I will focus in particular on two types of networks: transportation networks and computer networks. So at the end of the day, from a modeling point of view, they have a lot of things in common. They can be modeled as directed graphs. In each arc of these graphs, there are travel times. And these arcs suffer congestion. So the travel time increases with the number of, with the flow that traverses each arc. And in these networks, there are multiple agents. So in a transport networks, the agents are travelers. In a computer networks, the agents in my talk will be a pair of TCP sender and receiver. First of all, please interrupt me to ask questions, to say, criticize me if I say anything wrong, and on this kind of stuff. I think we have 1 hour in total. So I think I will not, I'm not sure I will go the part regarding the computer networks. It depends. In that case, we can set up another talk next time. So a small game. So what do you see? No, and this, understand? And this, no, and now is it a bit better? No, now maybe it's a bit more clear. So this is a painting of Georges Signac. And the pictures that I showed before are just details of this painting. This is just a small game to say that sometimes if you want to understand something, for instance, what happens in a network, sometimes the right approach is not to focus on just single elements or like a single traveler or a single TCP pair. And it's better to find some more macroscopic explanation, some macroscopic model of the phenomenon we are observing. And this is what I'm going to talk about today. So first I will introduce some formalism about traffic engineering, and then I will talk about this collective behavior that emerges in transport networks and then in computer networks. In both cases, what I would like to show is that at the end, each agent in these networks try to be selfish, to optimize its own objective function. But even if these agents don't know, they are actually optimizing some centralized objective function. So they don't know, but they happen to optimize something that is a single objective function. And this is what I call collective behavior. And so I will give some generic classic definition in transport networks, like Wardorf equilibrium. I will show how this Wardorf equilibrium can be described in terms of a centralized optimization problem. And I will talk about the Grice's paradox and how we can cope with it. And then when I will talk about computer networks, we will have time, I will discuss a bit how to model TCP in a very approximate way anyways, and how also in this case we can come up with a single centralized optimization problem that describes what single agents do. So most of the material are taken from this very nice paper, it's from Frank Kelly, and then okay, I added something and I took the liberty of trying some different things that I will tell you. And so Franchelli is a professor at Cambridge University, and he worked in computer networks, so in British Telecom. He could decide dynamic alternative routing, and also in the Department of Transport. So it's the demonstration of how these tools can be applied in both types of networks, almost indifferently. And okay, he received a lot of awards. And so some notation. I will denote with the I the set of links, and U and V the nodes. And so with R, U, V, I denote a set of all possible routes from node U to V. And R is the set of all routes. So it's the union of all routes from all origin and destinations. A is a matrix called the link route incidence matrix. So each element JR is equal to 1 if link J belongs to route R. And then we have these origin destination flows. So for instance, FUV is the flow that wishes to go from origin O to destination U. So for instance, the number of travelers who are willing to go from U to V. This can be travelers per hour or packets per second, requests per second. So this usually is considered an input to our problem. This is what the agents want to do. And then these flows can distribute across several routes. So if there are a set of routes to go from U to V, well, a part of this flow willing to go from U to V will go to a certain route R, another part to a certain route R prime, and so on and so on. And with the bold X, I will denote the vector of all the flows on all the routes. Oops. So these are flows on routes. Then we may need to calculate the flow on each link. And it's easy. I mean, this is the formula, the summation. I don't know if online you see my mouse. Yes. Okay. So actually, you take, so with this AJR, you select all the routes that contains J, link J. And so here you are summing the flow on all the routes that pass by J. And the result is the flow you have on link J. And okay, with the bold Y, I denote the vector of all the flows on all the links. And then we have delays. Delays are a function, so the delay on link J is a function of the flow on link J. And we will assume that this function is strictly increasing. This is the only assumption we need. Then in reality, we know that this function most of the time is convex. For instance, here is the classic diagram that relates the flow on a road link with the travel time on that road link. And on the right, this graph relates the average arrival rate of a link with the expected link time. Okay, so, but in general, we just need the delays to be strictly increasing. Okay. Questions on the notation? Okay. So let's define what is the Warren equilibrium. So first of all, we say that the route is so with the given a certain set of flows X, a route is the shortest, a route R is the shortest if whatever other routes R prime you consider, the delay on R prime is larger or equal to the delay on route R. Okay, simple. Of course, you can have several short routes, not necessarily a single one. And so, in general, we have a set that we call R star, routes that are the shortest to go from U to T. So we say that flows in a network are at Wardrop equilibrium if every OD pair uses only its shortest path. So, for instance, if you have a network in which to go from U to D, you have two routes, one that takes 3 minutes, the other 5 minutes. And there are some people taking the routes with 5 minutes. We are not in equilibrium because there are some agents, the ones that are in the 5 minutes link, that have the incentive to change route and to go to the other route that is just 3 minutes. So to be at equilibrium, we need all the agents to be okay with their current choice. For them, it should be impossible to improve the travel time by changing routes. Yeah.
Is it a vector one or is it
it's a strictly graded. Yeah.
This is one because
Yeah.
it is zero.
Yeah. So this is XR greater than 0. Yeah.
In practice, in this travel time or function of decisions.
Yes.
And so is it taken into account?
Yes, so the travel time is function of your decision and of the decision of all the others. Because if you are in a route, the travel time in that route also depends on the other people choosing to travel across the links that are in the route.
But then I don't understand how the framework. And so in your example, you were saying that if you have two routes with a certain delay time, you choose the shortest.
Yes.
But, I mean, how does this account for this delay problem?
So in practice, for instance, when you do transport simulation, you have to do many iterations where you initialize agents with a certain initial decision of the routes. Then you compute the delays that result from this choice. And then everybody takes another decision based on the travel times. And so the flows on routes change again. And so we recompute the travel times, and then you make another round of decisions and so on and so forth. And what happens in simulation is this day-to-day learning that is hopefully after many iterations of route choice and computation of travel times, you will arrive at the Wardrop equilibrium after these iterations. They are called the day-to-day learning because they sort of imitate what people would do if they didn't have general information about the network. They try one route, then they see that it takes a longer time than the other. They try another route next day, and so on and so forth.
So if suddenly all agents change at the same time.
In simulation, you do so. All agents change at the same time. Here we will see that we don't need to do so, and I will explain this. But here you have another question.
Yeah, so I mean, like in the exercise, an equilibrium, an affecting does not always exist. And here you call a Wardrop equilibrium something because this iteration might oscillate or
yeah, exactly. In general, this might oscillate. So you hope that these iterations will converge to a Wardrop equilibrium, but they may not. But we will see that Beckman shows that we always have an equilibrium. But in general, here, we are not talking about the procedure, how to find this equilibrium with iterations. We are just defining what is an equilibrium. So suppose that you have a network, and then you have also a vector of flows on routes X, such that whenever a route is used, so XR is larger than 0, then that route is the shortest. In this case, you are lucky because the network is already in equilibrium. Even if you do other iterations, no people will change because no people will have a better route. So here, let's assume that this equilibrium has been given already. Or in any case, let's assume that we have a set of flows on routes, and we want to decide, is it a Wardrop equilibrium or not? We do this test here, and we check. If this condition is respected, we are at Wardrop equilibrium, otherwise not. So the question arises, so does the Wardrop equilibrium always exist, or it may not exist at all?
Just a question for this,
Yeah.
for this question.
Yeah.
In fact, the equilibrium is the vector x that satisfies this.
Yes.
And there is one which is always right. The equilibrium is the vector which is t.
No, because you have to respect. So all the flows. Yeah, all the flows. So if there are 10 people willing to go from B to B, then
I said I don't remember that you the x are fixed by the flow.
I have a question. So this flow deterministic of the difficulty.
This flow, I don't know if it makes so in my head. I will talk as this flow is deterministic, but I think it doesn't make a real difference if this flow is stochastic and what we discuss is the expected flow. I don't use. So let's assume it's deterministic. Let's say we have really 5 passengers per second in a certain link, and in a certain route, and 5 passengers per second in another route. This one is so. Yeah, maybe I understood your question. So yeah, but this does mean that at every second we have 5 passengers. This means that we have a process whose average is 5 travelers per second in a certain route, 10 travelers per second in another route, etc. But it might oscillate.
Sorry.
Yes.
Yeah. The agents that we are considering here are the packets or the requests. Aren't there the sources of these packets or the requests? Does that make a difference?
So in this case, the agents are, let's say, travelers. And we consider that these travelers are not considered singularly, but they are considered as flows. So it's like a mortadella of travelers that we can split 0.5 in a route, 0.5 in another route. So in this, but these flows represent travelers. In a computer network, these flows would represent pairs of origin and destination, not single.
Right. So it's then equivalent to consider that there are the sources that may learn.
The sources. Yeah.
Okay.
For you, the sources are travelers willing to go from U to V. Yes.
All right. Okay. Thanks.
Okay. So yeah, the question is, does Wardrop equilibrium always exist? And if yes, can we compute it easily? Well, the answer came from Martin Beckman, who was professor at Chicago, Yale, Munich, etc. And he discovered, let's say, this theorem here. So if the travel time on a link are a strictly increasing function, then a Wardrop equilibrium always exists and can be found as a solution of this multi-commodity flow problem. And so here it's a we are this optimization problem has the vector of flows on routes as decision variable, as well as the vector of flows on links as decision variable. And the objective function is a sum over all the links of a sort of cumulative delay on link J. So you see, it's not simply the sum of the delay on each link, but it's the sum of the integral of the delay on each link going from 0 to yi, which is the flow on that link, so yj. So this is the optimization function, and then the constraints are, okay, this one, the number 3 is that all the flows might be satisfied. The 4 is that, okay, to get the flow on a certain link, we just take all the routes that pass by that link and we sum the flows on those routes. And then we also have that the flow cannot be negative. That's all. You see that there is no capacity constraints here. We imagine that there is infinite capacity, but of course, if there are too many people on a certain link, the delay can explode up to infinite. There are also versions of this problem that are capacity. Again, it's the same thing. So this result is very powerful because we started with the decisions that were taken by each agent, and the agents don't care, but they are actually behaving as there was a central authority that was dispatching flows in order to optimize this optimization, mysterious optimization problem. And so I think in those years there was a lot of enthusiasm about this kind of results from selfish decisions to collective behavior. And so Martin Beckman, in this article or book in which he introduced this finding, was saying a well-known characteristics of the equilibria encountered in theoretical mechanics is that they may be regarded as solutions to certain extreme problems, a fact which has occasionally given rise to some speculations about nature's grand design. Whatever the merits of theological interpretations, the possibility of formulating an equilibrium in terms of maximization is a useful piece of mathematical information. So, okay, there are people that can look at these results saying, okay, wow, it's philosophically interesting. He was more practical. He says, I don't care about the philosophy or the theology. For me, it's just a way to compute the word of equilibrium in an easy way. So yeah, I was talking about the similarity between Nash equilibrium and word of equilibrium. We have this fact of having multiple agents at equilibrium. No one has the interest in changing its decision. This is in general true for Nash equilibrium, and in one route, this decision is just which route I should take. So they seem the same thing. Actually, for some reason, they are not exactly the same thing. I'm not an expert, so I cannot tell. So I just took this sentence. Although the solution concepts are different, a Wardrop equilibrium can be viewed as an instance of a Nash equilibrium in a game with a large number of players. So I let people think about these people that know about this. So I wanted to show you why this problem is actually, so the solution of this central optimization, of this single optimization problem, is actually a Wardrop equilibrium. And so we need a bit of computation. So I hope you still see my screen.
Yes, we.
Okay, first, let's observe that this function here, objective function, is a sum of different terms. So if we focus on a single term, this is an integral of a strictly increasing function. And such a function is always convex. And so the sum of convex function is also convex. So the problem that we have in front of us is a convex problem. So we can use the Lagrangian methods, and what we will have is an optimal solution. So let's use the Lagrangian method. So the Lagrangian method, you define, is it too small to, I don't know,
Okay.
it's okay, I don't know online, I hope also it's
Yeah.
okay. So, so let's define the Lagrange function. So we have, the Lagrange function is a function of the original decision variables, as well as sets of Lagrangian multipliers. And let's see what is this function. Actually, it's the objective function that we have, like j, dj, dw. So I copy the objective function, and then let's say insert these constraints into the Lagrangian. So in some sense, I'm allowing these constraints to be violated, but if there is a violation of these constraints, I will pay a penalty because my Lagrangian will be higher. So let's write this and then we'll see. Maybe not I can do. This is better. So now let's write this constraint here. B and B. So these constraints. So we have one constraint per each pair of U and V. Okay, so I'm writing a Lagrangian multiplier per each pair of U and V, and here I'm rewriting these constraints. So I will not explain the rationale of Lagrangian method, but I just do the procedure as it is. So then I report these other constraints, which is J, mu J, and R, A, J, R, X, R, minus Y, J, minus, so the last constraint is this one. Okay. Okay, so this is the Lagrangian function. I wrote it. Now, the Lagrangian method says, again, I'm not an expert of this, but says that the optimal solution of the original problem, using the fact that the original problem is a complex problem, can be found by imposing some conditions called KKT conditions. KKT conditions. Okay, so the first conditions are called the primal feasibility conditions, and these are just the constraints as they are. Constraints, let's say 3, 4, and 5. 3, 4, and 5. These are primal feasibility conditions. Then we have the dual feasibility condition that imposes that this multiplier gamma R must be positive for all the routes. If I say something wrong, please tell me, or if you want to explain more, let's discuss. And then the classic thing is to compute the derivative and to set it to 0. So we compute the gradient of the Lagrangian function, and we set it to 0. So let's compute the gradient of the Lagrangian actually let me complete it on the right. Yes. Okay, that's okay. So gradient of the Lagrangian with respect to yj. Sorry, I'm not very agile with this thing. So okay. This, and I move it close to the Lagrangian. Yes. Okay. So derivative with respect to yj. So here we have the integral that becomes that okay, this derivative is 0 for all the j prime different than j, and so from the sum we just take the term corresponding to link j, and the derivative of this integral here is simply the content of the integral. So it's dj yj. I hope everybody agrees. Minus, so this term has nothing to do with yj, so the derivative is 0. And here the derivative is -1 multiplied by mu j for the link j in question. For all the other links j prime, the derivative is 0. So it's mu j equals to 0. Okay, from this we learned something about the weight, the Lagrangian multiplier with mu j. So we learned that it is actually equal to the j yj. Okay. Now to compute the gradient, we have also to, and we repeat this for all the links. Then we have to compute the derivative of the Lagrangian. Okay. Voila. With respect to xr, which were the other decision variables. And so, first term, nothing to do with r. In the second term, the derivative is, in the second term, the derivative is this one. Let me specify and then I will explain. Mu. Such that r, let me write it and then I will explain why. Multiplied by derivative of xr is simply 1. Okay, here pay attention that
there is a minus at the end.
yeah, there is a minus. Thank you. So here pay attention that in this sum, so here there are all the routes, okay, but actually when I select a certain route r, all the routes that are different than r are derivative 0, and so for all the right these terms will all have derivative 0 except one, that is the route that I'm choosing, and so at the end this mu this lambda uv that I will preserve is the one of which route belongs.
I don't understand why there are not many ones. Because you may have different pairs of U and V. Well, it's not the same route.
So imagine, so let's do it in loop. So I'm saying I want to do the derivative with respect to xr. So I enter the derivative here. Actually, let's do it. It's here the derivative, then I enter here, I enter here. Here the derivative is always 0. Minus the derivative like that. Okay, and here only one term will survive, and we have derivative 1, and it's the r that I'm considering.
My question was more on the first zone on unwittingly, but on unwittingly, I think you cannot have a route that is 14 pairs of.
Right. So
This
each.
is what I was thinking.
Yeah. So each route is connecting only one pair of origin and destination. So this is why only one term lambda UV will survive. So yeah, if you do the computation manually, you will realize more. If I try to explain even more.
When I started to ask the question, I was not thinking about the constraint that the endpoints, the route has only two.
Yes.
There's only one pair of endpoints.
Yes. Yes.
This wasn't just.
Yes. And okay, and then here the derivative with respect to R is equal to plus J mu J, and here the derivative with respect to R is J I J R. Okay, manually. Gamma R, because all the other R prime different than R will disappear. Is it okay? Then we set it to 0. Okay. Now, from this last equation that I wrote, we learned that the Lagrangian multiplier is actually equal to this thing that is write it. IJR mu R minus mu V. Let's write it like this, mu VR. This is the pair of origin destination which contain the route R. Okay. Okay, and we know from the dual feasibility that gamma R is positive, non-negative. So gamma R non-negative. Okay, and so this means that mu, lambda mu VR is less than this thing, AJR mu R. Now, AJR. I think I did a small mistake. Yeah, here it's mu J. Mu R doesn't make sense. So here I'm doing the derivative, and here it's mu J, not mu R. It was an error. So mu J. And so mu J. Okay. Sorry. Mu J. Now we understood that mu J was equal to the travel time on mu J. So instead of mu J, I write directly dj yj. And actually, this is the sum of the travel times on all the links which belong to route R, right? So in other words, this is the travel time on route R, which depends on the entire flows. Okay. Now, look at this. This is very interesting because we understood that this Lagrangian multiplier mu R has a meaning because it is a lower bound on the travel time on any route R which connects UV. Thanks to this inequality here, right? We saw that the travel time on any route connecting U and V is always larger or equal to this lambda. So we are happy because we found the lower bound on all the transtempts on all the routes. And we can exploit this thing. Because now let's take the routes that are used. So if route R is used, then XR is larger than 0. And thanks to yes, so I forgot to write another of the conditions of the AKT, that is the complementary Laplace, which imposes that gamma R XR it must be equal to 0. Okay, this was another condition that I forgot. So we know that if a route is used, its XR is larger than 0. So gamma R must be equal to 0, right? And so yes. Now, if we take this thing here, we can rewrite saying, we can rewrite saying 0 equal to J, A, J, R, mu J, minus lambda, there I can put in this sign here. And remember that this, we computed it because this is the travel time on link J, thanks to what we have found at the beginning. And so we had understood that this sum was actually the route, the travel time on the route. So we understood that if a route is used, its travel time is exactly equal to the lower bounds. So in other terms, if a route is used, the travel time is the minimum possible. So this means that if we solve this optimization problem, we will have a set of flows such that if a route is used, this is the shortest route. So in other terms, solving this problem, we obtain a Warthoff equilibrium. Is this clear? So it's actually elementary analysis that anyways give rise to a very nice result. Yes.
We started from the global optimization problem.
Yes.
And showed
Yes.
that it leads to the Warthoff equilibrium, but if you depart from the Warthoff equilibrium, can you show that the solution will solve this problem?
Yeah, the point. I think that yes, but I'm not sure. I think that in this, it's not even an article, it's a book. I think he does the two directions. So he says that a certain flow, a set of flows is a Warthoff equilibrium if and only if it can be computed as a solution of this optimization problem. But I'm not sure. I just selected this direction because it was easy to show. Okay. Questions on this? No? Okay. So I don't know how much time. Yeah. Yeah. So another thing is, of course, the solution of this problem is unique because the problem is complex. And so the question is, are there other equilibria that cannot be computed as a solution of this optimization problem? And this comes back to the question of Francois, and I don't remember. Yes, 5 minutes. 5 minutes. Okay, so I will just talk about the brass paradox and how the government can correct the brass paradox and why it makes sense for the mayor of Paris, what's the name? Araldo to close some parts of the periphery. People say, oh, there will be more traffic. No, actually, there can also be less traffic. So the Brass paradox shows that, yes, the Wardrop equilibrium is an equilibrium in which every agent is good because it cannot do better than it is actually doing. But this equilibrium can be very bad from a social point of view. Because at the end, we are minimizing this mysterious optimization function that has nothing to do with social good. And so, yeah, selfish agents can lead to an equilibrium that is bad. And the Brass equilibrium shows this by showing an example. So we have an original city with 4 links and a set of travelers, so flows of travelers which willing to go from south to north. And so there are 4 links. Then the mayor says, okay, I want to get more votes. And so I want to build another road from west to east. And so everybody will be happier because everybody will take less time to go to work. Brass showed that instead this is not true. Actually, if you compute the Wardrop equilibrium on the left, you have on average a travel time of 83 minutes of a unit of time. While if you compute the Wardrop equilibrium on the right, you have an average travel time of 92. So this is counterintuitive, but yeah, adding a resource, you worsen the things. Because now that there is another road, it will be convenient to use this road. And it will be convenient to use this road up to a level in which it's better to use another route that doesn't pass through this road. So before discarding this road, you have to go to a point in which the congestion is bad. Because if the congestion is not so bad, you still have the incentive to go to that new road. And in any case, trust me, if you do the computation, this is the new travel time. And so, how can we solve this thing, this situation? So one thing that one would say is that, okay, it suffices for all the travelers to have an agreement and say, okay, the mayor built this link, but he's stupid, so let's do an agreement. Nobody will have to use this link. Okay, there is an agreement. And if everybody respects the agreement, we have a travel time of 83, the original one. But there is a link now that is free. So if you go there, you go very fast, nobody's there. So for sure, there will be one traveler that will say, okay, this time I will go here, I will go fast. But also 2 travelers, 3 travelers, etc. Et so the agreement, of course, is not stable because there will be someone that will be better off using this link that is free. And this will happen until the level of congestion will become so bad, as in the previous case, that nobody will have the interest in using that link anymore. So, okay, the agreement between travelers is unreasonable. Another thing is that, okay, there is a dictator that says, okay, there is a link, but you will not go there. So when you have this tragedy of commons, when multiple agents lead to an equilibrium that is bad, one solution is the dictator says to each agent what to do. But in particular in transport networks, this is badly seen. So the mayor would lose a lot of votes. So another thing is tolls. So another thing that you can do is to perturb the cost function by adding another term. So far, travelers were only observing this travel time B. But now we can add an additional cost that I call MJ on each link. These can be a toll. And you see, this is, in my case, proportional to the flow. So you pay more as more traffic is there. Then, okay, notice that I'm summing the time and toll that is euros. But you can compare between the two by multiplying, by dividing by the value of time. So if the toll is 20 euros and you gain, and your value of time is 20 euros per hour, well, by paying 20 euros is like adding 1 hour more on the link. Okay, or this M can be artificial additional time that you can add in the link. For instance, you can put traffic lights that are useless. It's just to increase the travel time, worsen the travel time on the link, so as to go to an equilibrium that is better than usual. So now, if we have this cost, that is the sum of the original travel time plus this additional, so call it toll. Now, all agents will not try just to optimize the travel time. Will instead try to minimize their cost, generalized cost. So we can repeat the same reasoning, and we obtain a new equilibrium. Now, can you imagine a way to setting tolls so that the new equilibrium also minimizes social cost or maximizes social welfare? So one thing that one can do, and I think this is, maybe it's not official, it's not in books, but this was so easy that this is what I did, is that, okay, on the left, we have the original problem. On the right, we have the problem with the tolls, in which instead of travel times, we have overall cost. Now, I want to decide a structure of MJ such that this new objective function is actually the average travel time suffered by all the agents. So I want my objective function to be this one here. So I want to minimize the travel times. Here I'm weighting the travel time by the unit of traffic that is going to that link. So in other words, this minimization here is the average travel time suffered by a unit of traffic. And I want to minimize this. I'm assuming that this is the social good, having a low per traveler travel time. And so at the end, minimizing this is equal to minimizing this. Okay, this is equivalent to minimizing this function without the f, that is a constant. So now I want to find an MJ such that the sum of integrals of these things is equal to my social objective. So I have the computation to do so, but maybe there is no time to do the computation. But by deriving on the right and on the left and doing some basic things, you discover that the optimal toll that leads to a socially optimal equilibrium has this form here. It's proportional to the flow. So the more the flow, the more you have to pay, but also proportional to the sensitivity of the link. If a link is very small, so few additional cars implies an explosion of travel times, then the toll should be higher. Okay, so this is the optimal toll. If you do so, if the mayor puts this toll, you have a socially optimal equilibrium in terms of travel time. So this is why those are not so bad. Okay, so I think I will finish here. So just a recap of what we did. So we just talked about transport networks. And so we talked about transport networks, and we saw that there are a lot of agents that are selfish, but at the end, what they are doing, even if they don't know, is to minimize an optimization problem. And we saw that the equilibrium that results from this may be bad from a social point of view. So the travel times of everyone are not the best one can get. But we see that we can perturb the costs on the means in order to recover the social optimum. This is on transport networks. The second part of the talk was about TCP networks. And again, I will just give it this. So TCP was a protocol that was built like empirically. It was built empirically. One Jacobs and others tried different things. They said, okay, let's take the congestion window, let's divide by 2 in case of one event, let's increase it by a small amount in case of another event. But all these things were found empirically, like a recipe, like a magician, like your grandmother can do an omelette. But these are the rules that make internet work today. So there have been a lot of studies to understand why these empirical rules work and what they are actually doing. And Kelly, no, or I don't remember who, found that actually, if you take all the internet with all the TCP senders and receivers, they find an equilibrium that is the solution of this optimization problem, where PR is the end-to-end delay on route R, and XR is the amount of flow on route R. And here there are capacities. But yeah, maybe next time.
Yes,
Because I had the same derivation with the Lagrangian multipliers and stuff to show that